Hi Mindsetters, and especially to you grade 11 geographers, and welcome to the continuation of Geomorphology. Today we'll be continuing with Geomorphology and discovering and discussing aspects of slopes as well as mass movements. In order for you to better understand the grade 11 geography content, you must remember aspects that were discussed in grade 10, as they are progressively increasing your knowledge about the South African topography. Let's jump straight into slopes and the aspects that you need to understand. To understand slopes, the key component is as follows: the overview of South Africa's topography. Remember, the word topography can be substituted with the term relief. We need to also understand the types of slopes, and these include whether a slope is either gentle or steep, and we'll discover more complex natures using topographical maps of convex and concave slopes. The slope elements, remember there are 4 slope elements on a typical slope. However, we'll look at various different theories in order to substantiate and tell us better how to describe and understand these slopes. Remember, characteristics of slopes deal with the description of being able to identify the different types of slopes on the South African landscape. And lastly, we'll look at slope development over time and the concept of slope retreat. Remember from previous lessons, slope retreat can also be regarded as back wasting. Here we will be looking at the various different theories that have been postulated in order to better understand the slopes and relief in South African landscapes. Let's start off with the topography of South Africa, and in understanding this, we will look at the overview of South Africa's topography. Remember the following key components. South Africa's landscape has been shaped over a long time, and this is essentially geomorphology, where the changing of the shape and form of the Earth's surface over a longer period of time. Movement below the surface of the Earth. In any geomorphological understanding, we need to ensure that we understand both the intrusive, which is within the Earth's surface, as well as the extrusive, which is on top of the Earth's surface, and these forces and how they shape and form the Earth over time. By the movement of water across the surface of the Earth. Essentially, these are your fluvial processes, and what we bring into our understanding is how water changes the shape and form of the Earth's surface, especially in South Africa. We understand the different layers of rocks and how they've been laid down over millions of years. Again, the time factor is coming into play. To continue, and then shaped by erosion. Remember, your erosional understandings have been started in grade 10, and we continue with it in grade 11. Different strata and rock formations have been eroded, and the topography that results from these processes. Grade 11 geomorphology is largely taking the South African landscape and helping you better understand how the topography changes over space and time. Let's look at a few aspects through the satellite image of South Africa. What you should be able to understand and recognize is the following. In terms of South Africa, our topography is largely influenced as follows. We have what we call the coastal plain. The coastal plain stretches from the east to the west and incorporates all those areas in South Africa that lie along the coastline. We have the low-veld region. The low-veld region serves as a border between the Mpumalanga province as well as parts of Mozambique. Further to that, we have the escarpment. Remember, the escarpment is made up of mountain ranges that stretch across from the east to the west of South Africa. Further to this landscape and topography, you should be able to recognize the following. We have what we call the Great Karoo, which forms part of the Eastern as well as Western Cape provinces, as well as the Little Karoo. Note these provinces are largely influenced by undulating or uneven topography, and this Great and Little Karoo areas are mountainous regions, and these mountains lie parallel to the surface of the ocean. A little part of the Karoo which lies parallel to the west coast is the Cedarburg mountain range. This is also found in the Western Cape. What you should also remember is this large area here, which forms the plateau, is largely called and referred to as the Kalahari Basin. So let's go over that again. Dominated by the Kalahari Basin over the plateau is one topographical region, followed by, in this instance, the Great Karoo. South of the Great Karoo is the mountain ranges called the Little Karoo. On the east, remember, is your low-veld region. These are some of the regions that you should be able to recognize in South African topography. Let's move on. Let's start our understanding of slopes by identifying and defining what a slope is. A slope. What is a slope? The angle which any part of the Earth's surface makes with the horizontal. To describe that to you, remember, the flat surface of the Earth is always referred to as the horizontal. The moment there's a deviation away from the horizontal, we refer to this as a slope. Any geometric element of the Earth's surface. When we refer to geometry, we are talking about angles, and any deviation away from the horizontal is an angle. This angle on the Earth's surface is referred to as a slope. Now we will look at types of slopes. The first type of slope we refer to is a gentle slope. A slope with contour lines that are spread far apart, very important, from each other. Any gentle slope, the contour lines are far apart. This even spreading is maintained in both up and down slopes. We have a photograph to describe to you and show you what a gentle slope is. If we refer to this particular area here of this photograph, you will see that it's largely a flat surface. This flat surface best describes a gentle slope. Let's look at a steep slope. A slope represented with contour lines close together. Remember, gentle slopes, contour lines are far apart. Steep slopes, contour lines are close together on a topographical map. And here's a photograph showing you a steep slope. Note the scarp or steep and how the angle increases away from the horizontal. This is best described by contour lines that are close together. Let's move on. Further to your gentle and steep slopes, we can also describe convex as well as concave slopes. A convex slope. A slope which becomes progressively steeper downhill. It can refer to an entire slope or part of one. Key components of a convex slope is as follows: progressively steeper downhill. On a map, the contour lines will be spaced closer together with a decline in height above sea level. Let's have a look at a contour map that describes a convex slope. You will note the following. We've got a diagrammatic representation of a convex slope. Note progressively steeper. This area here is your progressive steepness. On a contour map, it will be displayed as follows. Note the contour lines are far apart and then progressively become closer. This is best described as a convex slope. To describe a concave slope, it's as follows. A slope which becomes progressively steeper uphill. Note the difference. With a convex slope, progressively steeper downhill. With a concave slope, progressively steeper uphill. It can refer to an entire slope or part of one. On a map, the contour lines will be spaced closer with an increase in height above sea level. Let's look at a diagram to represent this. Note the concave shape. Note the gentle slope and the concave shape. How is it represented with contour lines? The contour lines start off being close together and progressively become widely spaced. This is best described as a concave slope. Further to our understanding of gentle, steep, convex as well as concave slopes is the following. We have what we call tectonic slopes. Now, as you may remember from your grade 10 geomorphology, tectonics comes from the term concept of plate tectonics, where we study the Alfred Wegener theory of continental drift. Slopes were formed during the process of continental drift, and we best describe these slopes as tectonic slopes. Let's have a closer look. These are formed through internal forces that result in folding, warping, and faulting. Again, forces which occur within the Earth's surface of rock masses or layers. Anticlines and synclines. To describe that to you, let's look at it as follows. An anticline is an upward or upward bending of the rock material. A syncline is a downward. Remember, anti, upward, syn, downward bending of the rock surfaces. And these are formed when layers of rock are folded, while horsts, which is another term to describe block mountains, and graben, which is another term to describe rift valleys, are formed when blocks of land rise or fall in relation to each other when faulting occurs. Now let's look at a photograph that best describes tectonic slopes. Remember, as we've discussed from grade 10 geomorphology, we are largely looking at, during the process of continental drift, how slopes were formed. And if we look at this particular photograph, it shows us tectonic slopes in South America. Remember, these types of slopes are formed during the process of continental drift, and evidence suggests that these slopes were formed accordingly and became attached to the different continents. Let's look further. The next type of slopes we will look at is depositional slopes. Deposits of weathered material, which can be also eroded material, which build up to form inclined surfaces, mounds or hills, when agents of erosion, example wind, water or ice, which has lost its energy of motion, lays down its load in a particular place. To gather this information together, remember, depositional slopes are largely formed through the accumulation of different eroded material. Examples are alluvial fans, alluvial cones, deltas, and sand dunes. All these aspects have been discussed in grade 10, and remember, the continuation suggests that now we have to understand these in terms of slopes. An example is the following. This is the best example to describe an alluvial fan. Note the following. All the deposited material is occurring at the bottom of the slope. This increases the angle of the slope, and all this material accumulates at the bottom. This formation we refer to as an alluvial fan, which is a depositional slope. Moving on to the next element. Now we will look at the 4 slope elements. Any slope has largely 4 slope elements. Any typical slope should contain the following types of slopes. The slope elements are as follows. A crest. We best describe a crest as a small concave shaped slope with thin covering of soil. Your crest is the upper limit of any slope element. This is followed by what we commonly refer to as a cliff, which can be also termed the Scarp Slope or the free-facing slope. It's a near vertical slope which is more than 80 degrees to the horizontal. Remember, your cliff can also be termed the scarp or the free-face slope. The third slope element is commonly referred to as the Chalice Slope. Other terms best used to describe the Chalice Slope is the scree slope or the debris slope. To describe the Chalice Slope, it's as follows. A slope with a constant angle and is formed of eroded material from the crest and the free face. Although not common on most slope elements, a nick point is a type of slope element. The change in gradient at the base of the scree slope. Remember, the nick point is a point on your slope element. And largely, your 4th slope element is the pediment, which is described as a low angle concave slope. Let's look at characteristics of each type of slope element. The first and uppermost of all slope elements is your crest. Remember the following. It is at the edge of the hill. It is convex. It has a thin layer of soil, and all weathered material is removed. Looking at the photograph to describe the crest is the upper limit of all slope elements. Note it's convex in shape. And note all the material that accumulates runs down from the first element, down towards the cliff, chalice, as well as pediment. Moving on to the next slope, the free face, scarp, or cliff slope. It is important for you to remember the different ways to describe this type of slope. It is firstly greater than 80 degrees to the horizon or horizontal. It has a hard layer of resistant rock. Loose material falls to the bottom of the cliff. The cliff retreats parallel to itself. So there's a lot of back wasting on the cliff. If we look at the position of the cliff, here it is here. Note the scarp slope and note the angle, which is greater than 80 to 90 degrees at this stage. So your crest is at the top, your cliff is your second slope elements. And also important is to remember that this is a layer of resistant rock that retreats backwards. The next type of slope element is your talus slope, commonly referred to as a scree or debris slope. The key element of the talus slope is as follows. It is a zone of accumulation. Therefore, it accumulates the material from the crest as well as the cliff. All the eroded material that falls from the crest to the cliff accumulates at the talus. It is a uniform slope. The angle of the talus is dependent on the nature and amount of eroded material that lands from the crest or the cliff. The next slope element that we have to remember is the pediment. It is a low angle slope and also can be described as a concave slope. The slope is not uniform and it is steeper closer to the talus slope. This is because largely of the accumulation of the material and therefore can form a nick point along the slope. The pediment increases as the slope increases backwards due to scarp recession. So upon looking at the diagram, you should note the following. This particular area here is commonly referred to as the pediment. All the material, as it accumulates along the talus, then falls to the pediment, and dependent on the nature and amount of erosion that occurs, the pediment's angle is formed. Now we will look at different types of theories that have been postulated in order to better understand the types of slopes across the globe. What is important is these studies are largely based in specific regions. So as you will see, these types of theories are not really applicable to all parts of topography around the earth. However, when postulating, certain factors that were common were taken into account. The first type of theory that we're going to look at is the slope decline theory. And this was postulated by W.M. Davis in 1899. Remember, the concept of slope development over time and the concept of slope retreat. What this theory serves to postulate is the following. The theory was based on slopes in what was to Davis a normal climate. His theory was based in the USA. The type of climate in this region was a humid climate. Davis described the slope as follows. The steeper slopes at the beginning of the process with progressively decreasing angles over time to give convex upper slopes and concave lower slopes. Key component. He assumed a rapid uplift of land with an immediate onset of denudation. Remember, denudation can be also referred to as back wasting. The uplifted land which would undergo a cycle of erosion. Key component, where slopes were initially made steeper by vertical erosion by rivers, but later became less steep, slope decline, until the land was almost flat, which formed a peneplain. Remember, there's two ways to describe Davis-Stokes theory in terms of pediplanation as well as peniplanation. Simply put, with Davis, his theories were on backwasting, and he described in terms of erosion how slopes retreated backwards. His theories were largely based in the USA. Let's look at the next one. Slope replacement theory by Walter Penck in 1924. His region of study included parts of Europe, which included the Alps and the Andes, and he made a study of changes over time of these great mountain ranges. The climate he studied in tectonic areas, and his theories were largely based from the theories of continental drift. How did he describe a slope? He described it as the maximum angle decreases as the gentler lower slopes erode back to replace the steeper slopes, giving a concave central part to the slope. Let's look at his changes over time. He assumed that the landscape started with a vertical rock slope. A vertical rock slope is our cliff, with equal weathering overall. As scree collected, which is your Chalice slope, at the foot of the cliff, it gave a gentler slope, which as the scree slope grew, replaced the original one. Here he looks specifically at the accumulation of material along the talus as well as the pediment and describe these slopes accordingly. Our last theory that we will look at is the Alsea King theory, which was based in 1948 and 1957. His theory is commonly referred to as parallel retreat. His region of study was in South Africa, and the climate that he chose was the semi-arid landscapes, also sea cliffs with wave-cut platforms. So we should stand to reason that the areas of the Great and Little Karoo became part of the Alsea King theory. How did he describe the slopes? He described it again as the maximum angle remains constant, as do all slope facets, apart from the lower one, which increases in concavity. What this simply means is that all the accumulated material along the pediment resulted in a higher angle slope. What changes did he notice over time? He assumed that the slopes had two facets, a gently concave lower slope or a pediment and steeper upper slope, which we will refer to as a scarp, also termed cliff, correct. Weathering caused the parallel retreat of the scarp slope, allowing the pediment to extend in size. Again, this theory largely influences our understanding of the four slope elements. These three theories help us better understand how slopes have resulted in the crest, the cliff, the talus, as well as the pediment. Let's look now at an activity that will assist us in understanding slopes. The question says, refer to the figure showing elements of a slope to answer the questions. You will note the following. On your photograph, there are the labels A, B, C, D, as well as E. A, which we can conclude is our cliff, followed by, our crest, which is followed by the cliff, the talus, as well as the pediment. E, which is a flat surface, is commonly referred to as a plane. The first question, identify the slope elements labeled A, B, C, and D. As we've correctly indicated, A is your crest, B is your cliff. Let's go back. There's B, which refers to this entire section here, which is at 90 degrees. C is obviously your talus. Note the talus slope follows from your cliff slope. And D, all the accumulated eroded material, is your pediment. The next question, describe, very important, slope element B. We noted that slope element B was our cliff. However, the best way to describe it is in terms of its angle. And we should say the following. Describe slope element B, angle greater than 80 degrees. Another possible answer could be free face or scarp slope. These two terms can commonly describe the cliff. Moving on to the next question. Identify at least one factor that promotes fertile soil in E. As we've previously indicated, E is your plane, which is followed by the pediment. Remember, the pediment is your low angle slope. When you have a slope that is almost horizontal, we refer to it as the plane. And the plane refers to the accumulation of all the eroded material. So hence, if it's accumulated eroded material, this would have to be the fertile soil from erosion. So identify at least one factor that promotes fertile soil in area E. We can refer to this as the accumulation of eroded material from the pediment. And with that, we've come to the end of the first session. We'll be joining you again for the second part, which includes mass movements. And welcome back to the continuation of Geomorphology, grade 11. And now we will move on to mass movements, the final section in Geomorphology. Aspects that need to be understood in mass movements are as follows. We must be able to understand the concept and causes of mass movements. Further, in our understanding, the different kinds of mass movements that occur on the Earth's surface. The impact, a key component of mass movements, on people as well as the environment. And what strategies are there to minimize the effects of mass movements? So, let's begin with what is a mass movement. If we look at the following photographs, you will note the following, and these are common occurrences in South Africa. Aspects like rock falls, where the great masses of rock material break away from its parent rock. This picture describes a mass movement that occurs and destroys environments and people's lives. Let's define mass movement. Mass movement is the downslope movement of earth materials under the influence of gravity. Any downward movement of earth, which is soil, which can be rocks, is referred to as a mass movement. It can also be described as the detachment and movement of earth material that occurs if the stress imposed is greater than the strength of the material to hold it in place. In wet regions especially, where there is a lot of rainfall, this type of movement occurs where soil breaks away from its parent rocks. These rocks fall hard and downward due to the influence of gravity. Again, any movement of the rock material is referred to as mass movement. If we look at this particular picture, we will see as follows. Note the rock material that has accumulated after a heavy mass movement. One of the aspects that you need to understand is that you must be able to describe the different types of mass movements that occur. And these are described by the nature and amount of rock material that is moving due to gravity. What causes mass movements? Mass movements or mass wasting is caused by gravity, a key component of any mass movement. On a mass of material, gravity exerts a force downward proportional to the amount of mass. Again, when we're referring to the mass, we're talking about the soil movement. Because of the effect of water, which is a key component of any mass movement, on a slope stability, many mass wasting events are triggered or hastened by heavy or extended rainfall. If we look at the South African climate areas around and the nature and amount of rainfall that is exerted in South Africa, we would expect the following. The East Coast, largely influenced by the South Indian High bringing warm moist air, results in a lot of rainfall in this area. Most mass movements occur along the east coast of South Africa. However, the Western Cape region also experiences rainfall due to your South Atlantic High and forcing towards it the mid-latitude cyclone. This component brings in a lot of water, which then mixes with the soil and creates these types of mass movements. What you should also remember, in the Highveld region of South Africa, there's a lot of mining that occurs, and this creates instability in the ground below us, and therefore this also can result in mass movements of Earth. Now let's look at the kinds of mass movements. Different types of movements of Earth are described as follows and termed as follows. The types of mass movements that occur generally around the Earth are referred to as follows: soil creep, solifluction, landslides, rock falls, mud flows, and slumps. Now let's look at the kinds of mass movements. The first type of mass movement is described as soil creep. Creep is the slow, continuous movement of soil or unconsolidated sediments. These are sediments that are not joined together over an extended period of time. Soil creep is a slow type of mass movement of loose material down a slope. Often the rate of creep is less than a centimeter per year. So when we're describing soil creep, we should remember that this, of all the different types of mass movements or kinds of mass movements, is the slowest and can only be detected over many years by looking for its effects on the landscape. This is commonly referred to as accumulation of the rock material, as we've studied along the Chalice and the Pediment. The first type and kind of mass movement that we will refer to is soil creep. Soil creep is the slowest type of mass movement. What causes soil creep? Creep is caused by repeated freeze-thaw cycles. Over a period of time, as climate changes, we experience freeze-thaw. This is largely the lowering of temperatures against the soil, which results in the soil becoming frozen for a period of time, and then during higher temperatures, releasing that energy and falling down. Particles are elevated perpendicular to the slope, but during the thaws, they fall straight down to a new position lower on the slope. So what you should be taking note of in this aspect is the soil creep is largely influenced through the difference in temperatures. Creep can also be caused by the build-up of pore water that allows material to begin to flow under the influence of gravity. Sometimes within rocks, there are pore spaces, and this allows permeability of the rock to increase the nature and amount of water that is stored in the rock. When rocks store water, the material becomes loose, and this accelerates the rate of soil creep. What are the effects of soil creep? In this case, creep causes fence posts, utility poles, walls, and other structures to lean over time. Commonly, when you're driving around your suburbs, as well as areas where power lines as well as telephone poles are located, you will note that they are existing at a slight angle. This is not due largely to defects in the construction of this particular infrastructure. However, due to earth movements like soil creep, you will find that fence posts as well as infrastructure generally leans over either to the right or left, dependent on the slope. And this forces us to rebuild this type of infrastructure. In some cases, Creep can be slowed or prevented by installing drainage pipes in soils that drain them and keep the pressures low. Here's a typical example of soil creep. You will notice the following. This particular fence leans over and it's existing on a slope. What has happened here is, over a period of time, the soil in this area becomes loosened and transports downwards due to gravity. This evidence is shown through the nature of the boundary wall that has been built across the slope. This is a good example of soil creep. Let's look at the next type of example to describe mass movements. The next example we will refer to is a kind of mass movement called solifluction. It is the downslope movement of soil over a permanently frozen subsurface. Here, solifluction occurs in areas of lower temperatures, generally furthest away from the equator. Solifluction is common on slopes underlain by permafrost. Permafrost is a term used to describe the freezing of water and soil as one material. Permanently frozen subsoil. During the summer, when the upper permafrost is activated, the waterlogged soil, that soil which still contains water masses, slowly moves downslope to form solifluction lobes or terraces. Let's have a look at the photograph. Note the solifluction picture, largely in drier regions where temperatures are much lower. This type of area will result in solifluction, where the soil freezes over and moves over a slow period. Just like soil creep, solifluction occurs over a longer period of time. And as you can see, this breaks up the type of slope that we are studying. Let's look at the next kind of mass movement. The next kind of mass movement is common in most areas of and around the globe. It is referred to as landslides. Let's describe a landslide. A landslide is the movement of rock or debris, which is your loose rock material, down a slope along one or more distinct surfaces. Landslides range in speed from 1 meter per day to as much as 3 kilometers per hour. Note the increase in the rate at which the mass movement occurs. We started with the slowest mass movement, which is your soil creep. Then we've moved to solifluction, which also occurs over a period of time. Now the rate has increased, and the type of mass movement that we're referring to is landslides, which can occur over 1 meter per day and as fast as 300 kilometers per hour. Note this picture, and we've seen areas that have collapsed in this nature. This is best described as a landslide. Note how the mass movement has occurred. What has happened here is that over a period of time, this particular soil has been loosened. It has accumulated the water material and become waterlogged. But due to the high nature of rainfall, this entire area has slid down due to the force of gravity. Note this particular area has impacted on human activities as well as environmental damage. Landslides is a much faster form of mass movements. The next type of mass movement that will be referred to is a mud flow. Now let's look at what we've discussed. We've started with soil creep, which is the slowest type of mass movement, followed by solifluction. Then we discovered landslides, and now we will discuss mud flows. Note, as we progressively move up the mass movements, the nature and amount of water in the soil is increasing. And this water loosens the material, which increases the rate at which these mass movements occur. Let's look at mud flow. Mud flows occur on moderate to steep slopes. Movement is generally rapid. Note the nature of the movement is increasing. Primarily fine-grained material, smaller than sand-sized particles. Here we're looking at much looser material that is subjected to movement downward due to gravity. may begin as shallow soil slip, which is commonly referred to as shallow slides in soil over rock that parallels to the slope. This is the loose material that exists on a slope that is in constant motion. Typically flows down slopes or follows drainage channels. Here's a typical example of a mud flow. Note the roofs of these houses and note the nature and extent of the damage. Mud flows occur on a larger scale, and these types of movements are especially common in your wet regions where the nature and amount of rainfall is much higher. The next type of mass movement we will deal with is slumps. The sliding of material along a curved surface called rotational slide or slump. Note, another term for slump is rotational slide. A common cause of slumping is erosion at the base of a slope. For example, coastal storm waves erode cliff bases, removing supporting material. Commonly where tidal waves occur, especially along coastal areas, we have what we call a slump or a rotational slide. This erodes away the mass areas of the coastal plain. The slump block rotates downward, producing a scarp or cliff at the top of the slope. In this example, remember, we're referring largely to coastal areas. Note the following. There's the original landmass, and there's your slump area. Note the rotated blocks that occur due to slumping. We will now look at all different types of mass movements as they occur. What we've got for you today is a graph. Note the aspects of the graph: fast, slow, moderate, and describing the soil, drier soil, wet soil, as well as moisture soil. Remember, this area here increases as we go outwards. So of all the different types of mass movements, we can regard rock falls as your fastest mass movements. Landslides also occur at a rapid rate, as well as mud flow. As we move away, note the following. The slowest of all mass movements is soil creep, as well as solifluction. Note also that when we're describing the type of soil, in mud flows you have generally more saturated soil with water. Note the high rainfall that describes the mud flow. Your moderate type of mass movement is regarded as earth flow. So, in this graph, we are able to describe rock falls as your fastest and also driest of all mass movements. The moisture level increases from rock falls to landslides to mud flows. In this example, as compared to creep, rockfall is much faster, soil creep is much slower. Note the hints to describe the soil creep: the movement of infrastructure like telephone poles or boundary walls. Solifluction is a much smaller scale movement over a longer period of time. Note it is much more slower than earth flow or mud flow. This type of studying material will help you better understand the different aspects of mud flow or landslides or rock falls or creep, slump, solifluction, as well as earth flow. These mass movements must be described in terms of the pace at which they erode, as well as how fast they occur, as well as the nature and amount of moisture in the soil. The most damaging of all mass movements is generally your mud flow, due to its rapid pace as well as nature and amount of moisture in the soil. Let's look now at the effects of mass movements. And here we're going to look at photographs that best have described these mass movements. As you can see, this is largely referred to as a mud flow. Note the nature of moisture in the soil as well as the destruction that has occurred. Large parts of livelihoods, especially impacting on people, have been lost due to mass movements. This is because of construction along steep slopes. incorrect geological studies have shown that when people construct on slopes that are not stable and especially susceptible to this type of mass movements, there is large loss of human life. And as you can see, this results in panic as well as unpreparedness of this kind of impact. Generally, you'll find that roads along major highways as well as secondary roads are susceptible, especially when they're built on slopes. As you can see in this photograph, this has resulted from rock falls as well as a break and crack in the surface below. The moisture level below this particular road surface has become saturated with water and resulted in the instability of this road. In this example, another typical example of a mud flow, here you find the entire slope has succumbed due to high levels of moisture and has resulted in a large loss of life as well as destruction to property. The environmental damage is not sustainable, and therefore people are always discouraged from building on slopes, especially where incorrect geological studies have shown that these particular slopes are suitable. However, they've become not suitable due to the nature and amount of climatic conditions, especially rainfall. Let's look at human impact on landslides. Specifically, excavations into a slope for a road or construction sites, creating flat areas at the base of a slope. However, it is also over the steepness of the slope, removing the basal support that can result in failure. Here we largely look at this particular photograph, which describes what has happened when the bedding plane on which these particular slopes were existing were removed in order for construction. Note the entire landslide, and what has happened is it has caused a major destruction on this particular highway. What incorrect geological studies show is that when slopes are not identified according to their steepness and the climate region in which they occur, this is a common occurrence. If we further look on, especially in areas of mining, as you can see, this particular open cast mine has resulted in an instability in the rock structures, and the entire landmass has become susceptible to a landslide. Note, there is no moisture in this particular landslide. Therefore, it is a landslide and not a mud flow. And huge masses of waste material then flow downwards due to gravity. Continuing with human impact on landslides, harvesting timber, especially deforestation, can also have an impact. Removing slopes, supporting material, examples trees and bushes. In areas where vegetation is removed, this makes the soil loosened and can be susceptible to as simple as soil creep as well as landslides. As well as creating roads affects the landscape. If superficial and sometimes subsurface geology is unstable, mass wasting often occurs. Urbanization also has an effect on slope stability. Remember, the construction and rapid urbanization of large areas in our country results in slopes instability, especially where the nature of construction occurs on these steep slopes. Grading hillsides, cutting benches for building homes greatly increases landslide potential. The construction of homes on unstable slopes has similar effects, changing the slope surface, the additional weight, homes and fill material, plus the added water. Here we find that there is a lot of construction on slopes. People are forced to build on slopes due to the nature and amount of sunlight, especially with regards to the slope aspect. However, like we've seen earlier, there are no risks, there are a lot of risks taken when building on these types of slopes. Sprinkler systems, septic tanks make formerly stable slopes unstable. Add heavy rain season and you have lots of landslides. So what we need to do is to take into account the nature of the climate before constructing on slopes. We will continue looking at strategies to minimize the effects of mass movements. Firstly, minimizing landslide hazards requires 3 steps. These can include the identification of the landslide potential areas. And here GIS comes into play with the study of the topography of the landscape and the nature and amount of the climatic regions in terms of nature and amount of rainfall and nature and amount of temperatures. Prevention of landslides as well as corrective measures when landslides occur. How do we identify areas of landslides? We study aerial photographs to determine previous landslides or slope failures, as well as field investigations of potentially unstable slopes. These are good research areas in order for us to determine the possibility of a landslide occurring in these particular areas. Continuing with strategies to minimize mass movements. Potential mass wasting areas can be identified by steep slopes. What you should be able to recognize is any steep slope is susceptible to a landslide. Bedding plains inclined toward valley floors, hummocky topography, which is largely referred to as topography that is bent, or slopes that are bent, irregular as well as lumpy looking surfaces, covered by younger trees, water seeps, and areas where landslides have previously occurred. By just observing the nature of the slope, we should be able to identify whether a landslide has occurred at that slope in terms of the vegetation on the slope as well as the moisture within the soil. The information is then used to generate a hazard map depicting the various landslides prone areas. Here GIS, your geographical information systems, come into play, and large parts of the world are generally utilizing GIS in order to prevent construction on slopes that are susceptible to these types of mass movements. Further on, we can control drainage by reducing the slope angle and reducing the landslide potential. Here, terracing slopes in terms of step-like structures along slopes prevents and minimizes the nature and amount of mass movements. Concrete intercepted drains can be constructed to contain runoff and prevent infiltration. Infiltration is one of the key components of major mass movements. If we prevent infiltration on slopes, like constructing concrete areas that will create more surface runoff, you will reduce the nature and amount of landslides that occur. Steep slopes can be graded into gentler slopes. A series of stair steps, which is commonly referred to as terrace slopes, can be created on very steep slopes. Engineering methods can be used to help prevent slope failure. Retaining walls, which is a key aspect of preventing landslides. Rock bolts, which requires drilling into the rocks and holding these rocks back on the slope. As well as shotcrete, which is infusing concrete into the rocks, are used to inhibit the slope failure. Wire cables as well as wire fences minimize the danger of rock falls. Especially in the Western Cape areas, these kinds of wire mesh areas have prevented, especially along Chapman's Peak, the major impacts of rock falls in the form of developing wire cables and wire fences that hold back the rocks as they fall down onto the Chapman's Peak area. Correction of some landslides is possible. This is accomplished by installing a drainage system. These kinds of drainage systems drain the water from below the surface and desaturate the soil and remove some of the moisture. This reduces the water pressure slope and thereby preventing further movement. The next aspect is the key to preventing damage from landslides is to identify and avoid developing landslide-prone areas, such as steep, unstable hillsides. However, if some of these areas must be developed, then building codes should be required. In South Africa, we have stringent building codes that prevent construction, especially residential areas, on these kinds of slopes. Remember, extensive efforts to ensure slope stabilization and vegetation of unstable slopes. So what we do in South Africa is provide codes for the construction on slopes. And remember, dependent on the angle of slopes, the construction will be limited to specific types of buildings. Continuing with strategies to minimize the effects of mass movements, we look at the following. Again, installation of drainage and runoff channeling structures. Key to any removal of moisture is construction of drainage. Benching and regrading of slopes to lessen their steepness. The key aspects here, which I'd like you to remember, is the terrace of slopes. Continuing further, the stabilization structures such as retaining walls, deeply sunk pylons, and backfill supports. What is encouraged, especially where communication networks like pylons, which carry huge amounts of electricity, should be underpinned at a greater depth in order to provide more stability of these structures. The good slope engineering is expensive, and therefore the temptation to cut corners is great, especially where we see the impacts of landslides. We should remember those types of engineering have cut corners and not fulfilled the correct geological studies. However, landslide damage is far more expensive, and estimates have shown that for every rand spent on slope stabilization, between 10 and 2,000 rands are saved over a longer term. So in essence, what we should be encouraging is before construction occurs, there should be correct geological studies done of the surface, especially where the construction is required on steeper slopes. This would minimize the impact of landslides and to a larger extent mudslides or mud flows, which would result in the loss of property as well as loss of human life, which can further impact on damage to the environment. And now let's look at an example of a mass movement and a typical type of exam question that you will have in either a test or an exam. The question says, refer to the figure showing the element of mass movement. And this element can be either one of the elements of mass movements that we've discussed. When looking at this particular mass movement, immediately we would be able to see the movement of soil onto a particular residential area. Key question, identify the type of mass movement shown in the diagram. It can either be a mud flow or a landslide. In this case, it has to be a landslide. The reason is because by observing the nature of the soil, we are able to determine that the soil is much drier. Only when water is existent in the soil does it become a mudslide or a mud flow. So the answer here is landslide. Describe how this type of mass movement occurs. After earth movements, soil is loosened and is able to move downwards. Due to gravity. The slope is unstable and rock materials are not binded. Let's look at the answer again. Describe how this type of mass movement occurs. After earth movements, for example, we could have aspects like folding and faulting occurring below the surface, as well as tectonic movements. soil is loosened. The loose fragments of the soil are pushed to the top of the bedding plane and is able to move downwards due to gravity. A key component of any mass movement is the force of gravity. The slope is unstable. As soon as gravity starts acting on the loose material, the slope becomes unstable and the rock material is not binded. The loose rock material loses its binding and then is forced to move downwards, as can be seen in this photograph. And that would afford you the full marks. Let's move on to the last segment of this type of question on mass movement. The question reads as follows. Identify at least 2 impacts of this type of mass movement and how it would impact on humans. In this example, remember we've identified landslides, and the question requires us to answer in terms of its impact on human activities. And firstly, we should state clearly that the impact would be largely on the loss of life. Any landslide can lead to loss of life. Further to this, we can say the impact can result in loss of employment and destruction of property. A further answer could be the impact will disrupt communication. Networks. And this will afford you the full 4 marks, although we've given 3 points. So in essence, what you need to understand is the following. In terms of this type of section on mass movements, your ability to recognize the different types of mass movements is important. Remember, we've discussed in terms of mass movements, the nature and amount of soil material that moves downslope is dependent on how fast it moves as well as the moisture levels in the soil. What we are discussing today is in terms of slopes and mass movements. A quick recap of the sections that we have covered. Today, we've started off with slopes. Your ability to understand what is a slope and be able to tell the different kinds of slopes. Remember, we have the following. We have a gentle slope, and the key component is contour lines are far apart. We have a steep slope, where the contour lines are much closer together. We've also been able to identify a convex and a concave slope, as well as been describing depositional as well as tectonic slopes. You must remember there are 4 slope elements: your crest, cliff, chalice, and pediment. Dependent on the nature and amount of accumulation of rock material, a nick point may develop on one of these slopes. We've also described in terms of slopes how humans impact on slopes. This section is largely dealing with mass movements. Remember the different types of mass movements. We've started with soil creep, which of all mass movements is the slowest and by far the driest of all soil movements. We further discussed solifluction, which also takes a longer period of time. Landslides, remember, is also a destructive force of mass movements. However, the moisture levels in the soil is much lower. We further went on to rock falls, as well as describing how rock falls, especially along the Chapman's Peak area, has been prevented due to the construction of certain ways in which to improve stability. We've also discussed mudslides, or what we also call mud flow, which describes the high intensity levels of earth movements due to the high levels of moisture. In essence, all these different types of mass movements impact on human activities as well as increase the nature and amount of environmental damage. Your ability to see these different types of mass movements is important. You must be able to see whether this type of mass movement contains high levels of moisture or not. You must be able to identify different types of strategies that will enable the reduction of these types of mass movements. Key components include the study of geological surveys on these types of slopes, as well as re-engineering these types of slopes in order to prevent these mass movements. And we've concluded with an example of a landslide and its impact on the nature and amount of people living in a particular area. I hope you've enjoyed today's lesson, and that concludes our section on geomorphology. Good luck, guys, and remember, these aspects must be described accordingly in order for you to get the full possible mark. Thank you.